Alrighty, everybody. Good evening. I'm here for test one review, and I see that many of you are there. And I am going to be starting in a minute. All right, so I think today I'm going to start with gravimetrics problem. I know there was a group of students who were working during tutorial and lunch on a couple of gravimetrics problems that were there on the quiz. And while I cannot really give out the quiz problems, I found similar difficulty problem for you to go over. So can I just ask, first of all, is this field of view good? If I write here, is it big enough for you? Can you see it? Like if I were to write, say, a problem here, because I thought I'll put it a little bit closer because last time it seemed a little farther. So if I were to write gravimetrics, is it showing up pretty good? Is this size okay? Yes. The board is fine. The bottom may be a little cut off. Okay. Oh, so it pretty much goes till here. So if I'm going this way, probably I can go. Yeah, I see it. So probably what I see, you see too. A little further down. Okay. Thank you, everybody. All right. So gravimetrics. So gravimetrics is a method where you are trying to find either the percent purity or a component of a solution and how much of that is present. And the way you find is by precipitating out that component, because when the ion is in dissolved solution, you don't know its concentration. But if you precipitate it out, dry out that precipitate, use mole ratios, then you can figure out how much of that is there. So let me take two problems and explain it. And first one is a level 1 problem, which is a simpler. And then I'm going to add a twist to it, and you can see how that changes the problem. So level 1 problem says we have, let's say, 2 grams of an ore. Ore is like a mineral that you get it from the ground, which may not be all pure. And this ore containing calcium. Okay. And to find mass percent of calcium in this ore, it was dissolved and reacted with HCl. The calcium ions formed as a result of reaction, RXN for reaction with HCl, were then reacted with a very scary looking chemical, ammonium oxalate, to precipitate out as calcium oxalate. So this calcium oxalate was a precipitate. The mass of calcium oxalate, PPT for precipitate, was found to be, let's say, 2.43 grams. What is the mass percent of calcium in this ore. Scary looking problem, lot of words, but if you think about it, it is rather simple. So this one, Forrest, is a reliable problem for gravimetrics. So let's go over it. 2 grams of an ore, it has some calcium, and you don't know how much that is, but you're interested in finding that because you need to find the mass percent of calcium in this ore. So what you did is this ore has, this ore has calcium, and you reacted the ore with HCl, which turned calcium into calcium ions, which then you precipitated out with oxalate to get calcium oxalate. You have 2 grams of this, and you know this precipitate was 2.43 grams, and they ask you for mass percent of calcium. The thought process is from calcium oxalate grams, you can get moles of calcium oxalate. You don't need to know these formula. You need to know the moles of this. And then you know in 1 mole of CaC2O4, there is 1 mole of Ca. How do we know it? If you look here, there is 1 here, right? And there is 1 here. So in 1 mole of this whole thing, there is 1 mole of calcium. And then you can use molar mass to get grams of calcium, and then you can figure out mass percent. Let's do the problem together. So take out your calculators, guys, and let's go. Yes, you will always be given, Talia, all chemical equations and formula that go with the problem. I've not been that thoughtful in the practice problems, but on the test, I will be thoughtful to give you the equation. And if you see that there is a need for an equation or a formula that's not given, feel free to ask. So we have 2.43 grams of CaC2O4. And using the molar mass, we know 1 mole CaC2O4. I'm going to erase this blank here to create more room. One mole of CaC2O4 is 128 grams of CaC2O4. And then we know in 1 mole of CaC2O4, there is 1 mole of Ca. And we know 1 mole of Ca is 40 grams of Ca. Quickly, calculate it, guys. Use your calculators and tell me, what do you get? I can do it as well. 2.43 times 40 divided by 128. And that gives you 0.7594 grams of calcium. And because total ore is 2 grams, and for mass percent, you get 37.968. So 37.97% or around 38.0%. So this is a level 1 problem because you were given, there was only one thing whose mass you wanted to figure out, right? You were given the precipitate and just using the mole ratios, you got the mass of that. Now how I can turn this into a level 3 problem. But before that, I would like to address any questions that you may have on level 1 gravimetrics problem. So Bhavik's question is when we can or cannot round our answer. Typically, if it is about approximation, within 5% is always okay. You should be writing your answers in 3 significant digits, unless the question says that watch your significant digits and write the answer. Okay, so now this was level 1. And if I had to add a challenge to it, here is what I'm going to do. Watch it carefully. Now, I will say there is an ore containing 2 things that contain calcium. Containing, let's say, a calcium containing compound as CaHPO4 twice plus CaCl2. How have I added challenge to it? Now I've added 2 places where the calcium can come from. And I would say now mass percent of CaHPO4 twice. So I've chosen one of the 2 things that are in this ore. Let's keep it 2. I don't know. I'm making up these numbers, so it might come out. Then the numbers don't match, but we'll see. So we dissolved the ore, reacted with the HCl. The calcium ions were formed, and now we reacted with the HCl. And then we reacted with ammonium oxalate, precipitated, and found the mass to be 2.43 grams. What is the mass percent of CaHPO4 twice in it? Okay, so how have we added the challenge, guys? We have now 2 compounds in here that can give calcium. Also, this is a level 3 problem because it doesn't say that they are present in equal mole ratio. We cannot assume that. Now, how would that change the thought process? 2.00 grams of ore, we get some calcium, but now this calcium is coming from 2 sources, CaHPO4 twice and CaCl2. So when you get the moles, you cannot say this. All this is not valid. So how you will go about it is you'll go till here, as you did in previous problem. Now figure out total moles of calcium oxalate. So divide 2.43 by 128 still. And that gives you 0.01898 moles of calcium oxalate, or 0.01898 moles of calcium, right? Now let's assume X moles come from calcium, X moles calcium come from CaHPO4 twice, and then 0.01898 minus X moles of calcium will come from CaCl2, right? Now we know the total mass, which is 2 grams, is grams of CaHPO4 twice plus grams of CaCl2. So 2 grams is equal to X moles of CaHPO4 twice times its molar mass plus 0.01898 minus X times molar mass of calcium chloride. So 2 grams is X times molar mass of calcium hydrogen phosphate. So it'll be 40 plus 2 plus 31 times 2 plus 64 plus 64. I think it's 232. Yes. 232 plus 0.01898 minus X times the molar mass of this is 111. Okay. All right. I'm going to erase this part to continue. So now 2 grams is 232x plus 0.01898 minus x times 111. Let's solve for x, guys. You solve it and I solve it here too. Yeah, the numbers don't work out because we're getting a negative number. But if I had done it right, you'll get certain moles of X and you multiply it by molar mass. This will give you grams of CaHPO4 twice, and then you divide it by total mass, which is 3 grams times 100. I'm sorry, guys, the numbers don't work out because we're getting a negative number, which we shouldn't be because I just made it all up. I made these compounds. I wanted to show you how the challenge will be there. I do want to make a disclaimer. Are you all listening carefully? Just because I'm going over a gravimetrics problem doesn't mean that on the test you will get a gravimetrics problem. I'm doing this because today we reviewed quiz 3 and there were a lot of issues. All the kids in both the versions struggled with a gravimetrics problem. So I want to put a disclaimer here that this is no indication that there will be a gravimetrics problem on your test tomorrow. But it'll be there sometime for sure, so we needed to clarify this. All right, I'll pause here for a minute to take your questions. Anything that you're still confused about? Anything else I need to do before I go to the practice test of test 1? Yeah, the total is 2 grams, Harshit. That is correct, Brandon. So after you find X, you multiply by the mole mass of the part that you're finding the percent and then divide by total. That is correct. So total is 2 gram. 2.43 is how much precipitate was formed of calcium hydrogen, calcium oxalate, which precipitated out the calcium. Guys, I would like to repeat again, just because I'm doing a gravimetrics problem here does not mean it is going to be on the quiz, on the test tomorrow, okay? You tend to extrapolate that. There may be, I'm not saying there's not going to be, but do not overemphasize because you have 20 learning objectives on which you will be tested on. Oh, sorry. My bad, Iris. And Harshit, that's what you were saying. I was thinking, oh, I got 2 grams everywhere. Yes, it'll be 2 grams. All right, I'm not seeing many questions anymore, so I would move on to the practice test for test 1. And I hope you all took the practice test. I had posted the key online. Are there any questions on practice tests that I can go over or any concepts based upon any learning objectives that you would like me to go over? I am going to erase this. Krishna's question, how do we figure out the formula for decomposition? You would not have to. I will give you, because here in the problem where calcium carbonate was decomposing, I did not write this equation, but on the actual test, you will be given the equation. And if I slip, you will let me know. So I will give you all formulas, all equations. You don't have to know any of those. Alan's question number 6. So aluminum nitrate, I will give you the formula for aluminum nitrate. Maybe I shouldn't use this. I should use a black. That works better. Is I would give you that aluminum nitrate's formula is this. Then you should be able to say that there is 1 aluminum ion. You don't even need to know the charge, and 3 nitrate ions. So total there is 1 plus 3, 4 ions. So when 1 aluminum nitrate breaks, it'll make 4 ions. So if the molarity of aluminum nitrate is 1.2 molar, the molarity of its ions will be 1.2 times 4 or 4.8 molar. So that was number 6. There will be a calculator and a non-calculator part of the test, Iris. That is correct. Whoa, Harshita. Okay, 3, 10, 12, 14B, and 14C. Okay, let's start with 3. Number 3 says the compound CCl4 has some properties like it's non-flammable and it was used in fire extinguisher. And based upon your knowledge of periodic trends, which is more likely to be used as fire resistant? So you know, based upon periodic trends, that if the elements are closer together or are within the same group, they tend to have similar properties, right? So you are looking for a compound with C. So PbCl2 is an ionic compound. It's got a metal. There's no metal in this. So we'll rule out PbCl2D. We'll rule out BCl3 because it's too far. Now let's consider CH4 and CBr4. CH4, carbon is bonded to 4 of hydrogen. In CBr4, carbon is bonded to 4 of bromine. Hydrogen is a very small atom. Bromine, being in the same family as chlorine called halogens, will have same property or similar properties as CCl4. So we will pick CBr4 for that question. That is number 3, guys. So I'm going to go in order. I know Harshita asked for more, but then Sunny asked for 7. Somebody, Shunali, asked for 5. So let me do 5 first, then 7. Number 5, to determine moles of copper in a sample of mixture, students measure the absorbance. So, Shunali, if you look at number 5, number 5 has the data where you see that the concentration is 0.025. 0.050, 0.100, 0.200. And you see that the absorbance 0.059, 0.235, 0.117, 0.468, and then there is unknown. So you see generally the trend here is increasing. And you also know that as the concentration of colored species increases, absorbance should increase. So more likely, the most likely error is if we switch these two around. Now there is a gradual progression as the molarity of the color absorbing species is increasing. So you can deduce C that the student labeled the cuvettes incorrectly, reversing the labels on 2 of the solutions. So the student reversed these 2, hence you're not getting a nice progression. Okay, so bunch of questions. So here is what I'm going to do. There is somebody who wants me to do number 4 as well. So I'm just going to go over all the problems. How about that? Okay, number 4 is they have given you the mass spectrum here on this. And the way I thought about it is this is non-calculator section, so you can't really calculate, but you see that the most abundant is 90 mass isotope, but 92, 94, and 91 are not insignificant. So it has to be bigger than 90. It will not be closer to 94. So it is between 91 and 92. But so if you look at zirconium versus niobium, I picked niobium to be the right mass, and niobium's mass is 92.91 and zirconium is 91.22. So will this be closer to 92 or 91? I picked 92 because if there is a 94 and a 92, the average will be closer to 92 versus 91. But because this is a non-calculator section and you are almost guesstimating, I will accept either of those two answers. But the correct answer is C and B. So 3, 10, 12, 14, 5, and then 7. The atomic mass of carbon given in the periodic table is 12.01 rather than 12 because carbon has isotopes. The only reason why average atomic mass is not a whole number is because when you take all of those and add them together, then you get a fraction, not a whole number. So you will pick the one that mentions isotopes, which is B for number 7. Then no one wants number 8. No one wants number 9. Madhav, I'll come to your questions in a minute. Then I'm getting to number 10. Let me read the question so I'm not missing anything there. Oh, somebody wanted number 9. I will do number 9 in a minute, Swara. So Bhavik says, just to make sure there won't be any impurities problem on the test related to mass. No, there will not be. If it says element, generally it is that. If it is an impurity problem, the problem will say as such. But if I'm giving you multiple peaks and I talk an element, then you can assume there is no impurity, Bhavik. I will do 10. Number 9, Janani needs to see number 9. Wait. Sure, no problem. First, can you explain number 9, 11, 12? Okay, all right. I'm on track. Okay, so number 9, I will do in a minute. 3, 5, 7. Did I do 7? Yes, I did 3, 5, 7. I'm on to number 9 now. This board's so rickety. Okay, number 9 says, what volume of 0.150 molar HCl is required to neutralize 25 mils of 0.120 barium hydroxide? Again, guys, in this, I will give you equation. So equation is 2HCl plus BaOH twice gives you BaCl2 plus 2H2O. So a question there, some of you may ask, why did you not give us equations here? Guys, I'm switching my mode because till last year, for past 8 years, students will know this because we did this before we did these problems. So this is just me making that switch to remember that you haven't done this yet. So this will be given to you. Now they ask you how much volume. So the thought process is, we know M1V1 is equal to M2V2. However, the mole ratio is a little skewed. So we need to kind of take care of that as well. So if you do M and V here, you can get moles of barium hydroxide. Let's start with that. So moles of barium hydroxide will be M times V. Molarity is 0.150 120 and volume is 0.025. So guys, if you're writing molarity, that is moles per liter, your volume should be in liter as well. And when you do that, you get 0.003 moles of BaOH twice. Now you know that 1 mole of BaOH twice is needed for 2 moles of HCl. So you have 0.006 moles of HCl, and you know moles is molarity times volume. We have 0.150 molarity of HCl. So volume of HCl will be 0.006 divided by 0.150. This is moles and this is moles per liter. So you get 0.04 liter or 40 mils. So that was question number 9. Swara and others, whoever asked this question, you guys are good with it? So Madhav's question, yes, it will be given if the substances are in 1-to-1 ratio for mass percent sake. You cannot assume a 1-to-1 ratio. If it is a 1-to-1 ratio, it'll be explicitly given to you. So Johnny, I did number 9. Carl wants number 10, and I'm getting to number 10. 10, 11, 12. Okay, I'll do rest. I get the idea. Okay. So let me do number 10. Number 10 says a new element with atomic number 116 was discovered. What will be? So 116, guys. Look at this periodic table. Okay. So this one is 112. 112. So 13, 14, 15, 16. 116 will be here under the oxygen group. That is a key piece of information. Okay. It'll be under oxygen group. Okay. So if it is under oxygen group, it will be S2P4. Now what else? It is in 7th period. And because they ask electron configuration of only the valence electrons, you don't need to write anything before it because valence will be only S and P, not D and F. So that is A. B, what is the likely formula with hydrogen? You know hydrogen forms +1 or 1. And this one has 6 electrons, 6 valence. So it will tend to have 2 minus. And when you crisscross these charges, it will be H2LV. C, the first ionization energy of polonium, which is right above it. So LV is here and polonium is right above it, is 812 kilojoules per mole. And they ask you, would the ionization energy be greater, less than, or equal to? It will be less than because as you go down, a group atomic radius increases because you've added more energy levels. So to remove an electron is easier due to lesser attraction from the nuclear protons. According to Coulomb's law, Q1, Q2 over R. If this R is increasing, then it's easier to pull it off. Let us see. Part D asks you for average atomic mass, and they have given you a mass spectrograph here. So in that spectrograph, it tells you that 291.2 mass isotopes relative abundance is 291 292.2 AMU's relative abundance is 3. 293.2 AMU's relative abundance is 5. So you convert them to percent abundances for atomic mass. So if you add up all the relative abundances, they come out to be 10, right? So percent abundance will be out of 100. So it'll be 20%, 30%, 50%. Another way to think about it is 2 times 100 over 10. In 10, it was 2. In 100, how much would that be? So that is 20%. Now, to get the average atomic mass, you take each individual mass. So first isotope is 291.2 AMU times the decimal fraction of its percent abundance, 0.02, plus 292.2 times 0.30 plus 293.2 times 0.50. When you add them all up, you get 292.5 AMU. That is its average atomic mass. That is question number 10. Sid, Krishna, that is correct. For number 9, you don't need the equation. If you can acknowledge that there are 2 hydroxides and there is 1 H+, so it will be a 1:2 ratio. Yes. So Natasha's question, why do you need this mole ratio M1V1 is equal to M2V2? Assume there is 1:1 mole because it's moles of acid is equal to moles of base. For a monoproduct, for an acid that has only 1 H, for a base that has only 1 OH, that is true. Moles of acid are equal to moles of base. But if your acid or base have 2 H's or 2 OH's, then that ratio does not hold good, Natasha. So you got to take that into mind. The ground electron configuration, Sravya, for LVB, you read the noble gas before that, which is radon, Rn, 7s2, 7p6, 7s2, 5d10, 4f14, 7p1, 2, 3, 4. Okay, Shravya, you got that? Hello, Christian. Do we have to know what aluminum nitrate is? No, that formula will be given to you, Christian. Could you repeat 10C? And it is on the video. So 10C is because as you go down a group, you increase the energy level. So atomic radius increases. According to Coulomb's law, the attraction between the nuclear protons is directly proportional to their charges and inversely proportional to the square of the distance between them. So if you increase the atomic radius, then the attraction of nuclear proton on the outermost electron decreases, so it can be removed easier. Is the percent of bar graph ever made with an element? Adamia, generally that is not done. If the problem specifically asks you, then yes, it can be done. I know on the worksheets, there were a couple of places where the problem specifically asked you to take the most abundant isotope as 100. Generally, in going from relative to percent, you do relative to percent, you just use ratio. If you're going from percent to relative, that's when you can take your highest occurring isotope as 100. 5F14 and 6D10. What period are we in? So Sravia's question, 1, 2, 3, 4, 5, 6, 7, right? This is 7th period. So it'll be 6D10 and 5F14. So I might have said it wrong, Sravia. If this is the 7th period, it is N minus 1D and N minus 2F. So it is 7S2, 6D10, 5F14, 7P4. Okay, so far so good. Now let's get back to the questions. So we did number 10. I know kids wanted number 11. So moving on to question number 11. 11 says a test tube containing calcium carbonate, and again this will have the equation calcium carbonate solid when heated forms calcium oxide solid plus carbon dioxide gas. This has to be given to you. So you have a solid calcium carbonate, you heat it up, and what happens is carbon dioxide gas escapes, and what remains here is calcium oxide solid. So they say the test tube plus CaCO3 was 30.08 grams, right? And they said the test tube became lighter by 4.40 grams. So what was it that made the test tube lighter? The carbon dioxide that escaped. So this is the mass of carbon dioxide. If you divide it by 44 grams, you get moles of CO2. And 1 mole of CO2 is 1 mole of CaCO3, and 1 mole of CaCO3 is 100 grams of CaCO3. And why do we want to know? So if you know the mass of this test tube and mass of calcium carbonate, and they're asking you just the mass of test tube, if you subtract calcium carbonate from it, then you get the mass of test tube. So you get 10 grams for calcium carbonate. So then you subtract from 30.08 grams, which is test tube, plus calcium carbonate, 10 grams, which is calcium carbonate. You get empty test tube as 20.08 grams. That is question number 11. Yes, Manju, that is correct. You will have to give a one-liner explanation for your question, and it's going to really matter because there are fewer multiple choice questions. So if you miss that, it will impact your scores. And I would like to see your thought process behind choosing your options. Okay. All right, so that was 11. Let me go back and see what all questions were being asked. So 12, Forrest. Okay. So consider the following equation. Number 12 is a stoichiometry problem with very complicated names, so that can throw you off. So number 12 gives you an equation 2FeTiO3 plus 4HCl plus Cl2 gives you 2FeCl3 plus 2TiO2 plus 2H2O. This is given to you. They say how much of this, when they say how much, they ask for grams of this can be prepared from 379 grams of ore. This ore is not this. This has ilmenite. This is called ilmenite. And the ore has ilmenite in it. How much? Only 88.3%. So if you do 0.883 of this, that much is the ilmenite in this. So when you do that, you get 334.7 grams of ilmenite or FeTiO3. And then using molar mass, 151.75 grams of FeTiO3 is 1 mole of FeTiO3. And you need 2 moles of FeTiO3 to make 2 moles of TiO2. And 1 mole of TiO2 is 79.9 grams of TiO2. And by doing that, you get 176 grams of TiO2. So if all of the ore was ilmenite, you did not have to do it. But only 88.3% of the ore is ilmenite. So you need to figure out in 379 how much ilmenite is present. Once you figure out ilmenite, then you convert it to mole, use mole conversions. But the percent purity plays a role in there. That was number 12. So to answer Talia's question, how do you know number 3 isn't A? Okay, because boron is far away from carbon. So if you look at the formula, it's CCl4. So you look in for a compound with C in there. That is why you wouldn't choose BCl3. Okay, so number 14, I will do all of it because I know there are questions on 14, but now there is a question on 13 as well. So Sarah wants me to do 13 and 14. Yes, Forrest, that much 5% error is there because I wanted to write in 3 sig figs. I rounded it. Yeah, you got that. Okay, Sunny, I would like to ask you because you're the only one who asked for number 13. Do you still want me? Oh, Sunny and Sarah. I'm not sure if Sunny asked for it. Sarah, do you still want number 13? I will do 14 and then I will do 15. Anyone wants 13? Can you type, please, if you want 13? Okay, let's do it. 13, 14, and 15. Okay, number 13. A series of dilute NaCl are prepared from stock. So stock is 0.100 molarity NaCl. You took 10 mils of this and you diluted to make solution A, right? So we'll do M1V1 is equal to M2V2. We took 0.1 molarity solution and we took 0.101 liters of it. And we don't know what's the molarity. And we made 250 mils or 0.250 liters. That gives you the molarity as 0.00400 molar for solution A. Then you took this molarity and you again made solution B. Again use M1V1 is equal to M2V2. You took 0.00400 molarity and you took 25 mils of it and you need to know molarity and 0.10 liters. So 100 mils. So molarity of solution B comes out to be 0.00100 molar. But you didn't stop here. You made a solution C and you took 0.001 molar, 0.020 liters of it, and you want to know molarity, and you made now 500 mils of it. And the molarity is 4 times 10 power negative 5 molar. Also, guys, in these problems that are sequential, kind of doing a flow chart way is helpful because it keeps your work clean and organized. Half the time, the battle is to seeing your own work and making sense of it. Karina, we did 11. You can, once the video is posted, you can go back and see I did 11 already. Okay, now on to number 14 and then 15. So that would have covered pretty much the entire test. I will put timestamps once the video is processed, so you can go straight to the problem. Number 14 said you had an empty beaker. I'm not going to put the weighing scale. You added metal M to it. And let's say you added metal M and then you added iodine and it formed Mi2. Now they say metal M is in excess, meaning all of the metal M did not get used up here, right? The reaction proceeds until all of iodine is consumed. So iodine is the limiting reactant. It got all consumed and there's leftover M. Now they precipitated out Mi2 and they got grams of Mi2. Now they ask you different things. So they have given you mass of beaker. They have given you beaker plus metal M. Beaker plus metal M. If you subtract beaker from it, you will get grams of M, but you know this is not going to be right because this will be all the grams of M, but all the grams did not react. Remember, there was leftover M. All of the I2 was gone. So really, to get grams of M, you have to do something else. We'll talk about it, okay? So to get, and then what they have is grams of Mi2 after 2 weighings, right? They also have mass of beaker plus metal plus I2, and then they have mass of Mi2. So if from beaker plus metal plus I2, you subtract beaker plus metal, what will this give you, guys? It will give you grams of I2 that reacted, right? So we do that for the first part because first part asks you moles of I2. So you take this mass, subtract the mass of metal from that, and this was 127.570 grams minus 126.549 grams, and that gives you 1.020 grams of I2, but they ask you for moles of I2. So 2 times 127 grams of I2 is 1 mole of I2. So this gives you 0.00402 moles of I2. So far, so good? Because in the body here, Krishna, it says the reaction proceeds until all of the I2 is consumed. That's how you know that all the I2 is used up. Okay, so read these. These things I know are kind of painful, but they will sneak in information or two in there, so they test your patience sometimes. Okay, now we got moles of I2. Now we need to figure out molar mass of metal M. Okay, so if we take mass of Mi2 and subtract mass of I2 from there, then we get mass of M. Okay, so mass of Mi2 is 1.284 grams minus 1.021 grams of I2. It gives you 0.263 grams of M. So we want to figure out the molar mass, right? So we know that 0.00402 moles we calculated. Moles of I2 means there would be, because there's a 1-to-1 mole ratio between Mi2 and Mni2, right? So it will also be same moles of Mi2, right? So we know that 0.00402 moles of Mi2 weigh how much? We know the mass of Mi2, 1.284 grams of Mi2. So 1 mole of Mi2 will weigh how much? That will weigh 319.40 grams per mole. So this is the molar mass of Mi2. Once we know the molar mass of Mi2, we know there is 1 mole of Mi2, right? Its mass is 319.40 grams. If you subtract mass of I2, 2 times 127 grams from this, you will get mass of M, which will be 65.4 grams per mole. And we know this is the molar mass of M because we know there is 1 mole of M in 1 mole of Mi2. So the key was to figure out the molar mass of Mi2 and then subtract the mass of I2 from there to get the mass of M. And the reason we cannot use the second minus first reading for mass of M is because there is unreacted M. They said all of the iodine was gone, but M was remaining. So we need to figure out mass of M by subtracting from mass of Mi2 the mass of I2. That will tell us how much mass of M was reacted. And because we knew moles of I2, we can figure out molar mass of Mi2 because we know that will be the same moles of Mi2. There are more than one ways of doing that, Brandon. So if your method gives you the same answer, then I would say yes. Yes, that is correct. Bhavik, here the first and second weighing are the same, but if the second weighing is a little different, then you can use second. 319, Iris came from getting the mass of 1 mole of Mi2. We knew 0.00402 moles of Mi2 weighed 1.284 grams. We knew how much Mi2 was in here. Using the I2's moles, because of 1-to-1 mole ratio, we also knew that was 0.00402 moles of Mi2, and then using ratios. If 0.00402 moles of Mi2 weigh this much, then 1 mole will make how much? And whatever the 1 mole weighs is the molar mass of Mi2. Any questions on number 14 before I go to 15? Krishna, I would like to know the context. Where are you talking about? Oh, are you talking about part C of this question? A student hypothesizes that the compound formed in the synthesis reaction is ionic. Propose experimental tests that you could perform. We have a whole like 5 or 6 learning objectives in the next unit on this, but the short answer is yes. If the substance dissolves in water and conducts electricity in aqueous form, but it does not conduct electricity in solid form, then that is an ionic compound. So 14C, Sarah, is in the next unit. That's why I crossed it out, but I just told you the answer of 14C. Okay, now I'm going to move on to number 15, the last problem on this. So number 15 is a lot of information. So copper reacts with 4HNO3 to form CuNO3 twice plus 2NO2 plus 2H2O. Each student in a class placed 2-gram mixture of aluminum plus copper in a beaker and a fume hood. Then they placed 15 mils of HNO3, 15.8 molar HNO3 in the beakers. Then they allowed the reaction and a brown gas came and copper ions were formed. So a lot of action happening. The students determined that the reaction produced 0.010 moles of copper . 0.010 moles of this, it will be 0.010 moles of copper as well. For mass percent of copper, you need to have grams of copper over total grams of mixture times 100. Grams of copper will be 0.010 times 63.55 grams per mole. And the total grams are 2 grams times 100. And that gives you a mass percent of 31.8%. So rest all was useless information. Jeremy is asking what will be the level 3 of this problem. Which problem, Jeremy? Is it number 14 you're asking? I would classify number 14 as a level 3 problem. It's a AP test level problem. It is as hard as it gets. Oh, 15. 15, they could do very many twists to make it level 3. Maybe they did not give you this, but they gave you some mixture where you had to calculate using percent purity, amount of copper, and then do it. They also, instead of giving this mole, could just do molarity and volume here. Or to add another level, they could say that the moles of these were calculated from yet another titration, and they can give you molarity times volume in that. And they don't necessarily in the titration and this don't react in a 1-to-1 ratio. So they can give you different mole ratios. So you have to first come up with moles of this and then come up with moles of this. So there could be multiple twists. They could add levels to figure out the moles of this. Those levels could be another titration that helps you calculate copper moles, another precipitation through which you get moles of this, or even impure sample in which some is copper and some is something else. So really the difficulty level can be increased by adding, not giving you this data and having you come up with this data one of the many ways. Alrighty guys, so that is 8:05. Tomorrow's test, Harshita, will be a little shorter than today's in terms of free response. So there are very many free response. 1, 2, 3, 4 free response question. I don't think tomorrow's test, I don't remember, but 2 to 3 free response, at least one less free response. And elements, remember, the most important thing is a good night's sleep and a bite to eat. Bring energy bar to eat. Your brain will be doing a lot of work tomorrow. Okay? You are so welcome, everybody, and don't get into a frenzy. You are okay. We got it. We've worked hard, and you'll be fine. I will timestamp and post this video as soon as it gets done processing. Thank you very much, Elements. Thank you for spending your evening with me. It is so good to hear that you found it useful. Oh, you guys are incredible. Thank you, everybody. I'm going to end the stream here.